some basic properties. One of the simplest properties is the double negation. If we do this, not A, we get A back, the original A. You can think about it as two wrongs make a right. The commutative laws. A or B equals B or A. And also A and B equals B and A. This means that we can actually change the order of the arguments for or and. And somehow, maybe if you need something to relate to, it is mostly like 5 times 7 equals 7 times 5. This law is about the same as this law. They are correct because of different reasons, but maybe if it helps you to remember, you can always think about it like this. The associative laws. A or B or C equals A or B or C. And the same goes for the AND operator. This one is somehow like this. 2 plus, in brackets, 4 plus 3 equals 2 plus 4 plus 3. This kind of law doesn't always apply. For example, if we think about exponenting things, then this law is absolutely not true. And another thing is that this law, the associative law, is not the same as the commutative law. This one is about changing the place of the brackets. You can say that we take the brackets from the right side and put them on the left side. It is not the same as changing the order of two elements. The distributive laws. This one is really interesting. A or B and C equals A or B and A or C. And surprisingly, the same happens if we change every OR to AND and every AND to OR. A and B or C equals A and B or A and C. This is somehow like opening the bracket in usual arithmetic. For example, 3 times 2 plus 5 equals 3 times 2 plus 3 times 5. This one might be a bit harder to believe. That's why I added a truth table style proof here, which we can check and make sure that the distributive law actually works. So here we basically check the first one, this equation. We try every different possibility for the input. The input is represented by 3 bits, A, B, and C. We just count over all the numbers of size 3 bits. It begins with 0 and we go until 7. We can say that this is 0, this is 1, 2, 3, 4, 5, 6, 7. Take a moment to see that the numbers that I counted in decimal correspond to the binary representation that we get from A, B, and C. And here we can see the two different sides of the equation. This row represents the left side of the equation. And this row represents the right side of the equation. So basically, it would be enough to just try every possible input and make sure that the output always equals. This table shows that the outputs are equal for every possibility. Let's just try one of those possibilities to check it, to make sure that you know how to create this kind of table yourself. Let's look, for example, on this input. A equals 0, B equals 1, and C equals 1. So what do we get? For this expression, A or B and C, we get 0 or 1 and 1, which results in 0 or 1, which is 1, just like listed here in the table. The other expression, the right-hand expression in the equation, is A or B and A or C. We know that A equals 0 and B equals 1. Also C equals 1. So the first clause here, A or B, is going to equal 1. And the next clause is also 1. So 1 and 1 finally equals 1, as listed here. And we have, for example, for this input, that the two sides of the equation agree. Both of them agree that the result should be 1. If any of those rows had a different output for one of those inputs, that would mean that the equation is wrong, but we don't have it here. Here we can see that for every input, the left side of the equation equals the right side of the equation. So we can conclude that definitely this expression equals this expression. Even though they look a bit different, they equal the same. They mean the same thing. Let's try again to look at this expression, but this time from a different point of view. I remind you that this equation is the distributive law that we've just looked at in the previous slide. We can see it here, the first one. Now we take another look at it. This time we are going to try to understand it using Venn diagram. Let me explain what we are looking at. We have the two sides of the equation. This part that we can see here is the left-hand side of the equation, and the other part at the bottom, this part, is the right-hand side of the equation. And we want to see the kind of picture that we get for each of the sides. Let's begin with the left side, which is the top in this painting. First we have A, which is this in the equation, and we can represent it as being one of the three circles that is colored by brown. We also have B and C, which is represented in a Venn diagram this way. B and C. The intersection of the two circles, the B circle and the C circle, is colored by brown. Now we finally have to invoke OR between A and between the expression B and C to get A or B and C. And we get this result, this picture, which is composed both of this circle, the brown A circle, and this small part, the intersection of the B and C circles. When we take OR over those two paintings, we get their combination. We can see here the circle together with this small part. Now let's try to look at the right hand side of the equation, and we are going to look now at the bottom of the painting. We have here A or B, which is just the A circle colored by brown together with the B circle colored by brown. And we are going to end it with this part, A or C, which is basically the A circle colored with brown together with the C circle colored with brown. When we invoke AND between those two paintings, we are going to take only the regions which are colored in both of those paintings. In the first example, from top, we can see that the result was that any region that was colored in any of the paintings was eventually colored in the result. But this time, when we use the AND operator, we are going to color only regions that are colored in both of the paintings. So definitely this region is brown in both of the paintings, and also this region, and this region, the central one, and also this region. And this one. This region is colored both here and here. So again we get this picture. Many mathematicians are going to say that this is not a formal proof. However, you can always use this kind of diagrams to aid your understanding or to help you prove things. It could really help you.